Hello. Today we will be continuing our lecture on global climate change. In the first series of lectures, we talked about primarily the main drivers of the global climate. So that was the carbon cycle and some of the other primary drivers, the climate drivers, and as well as the greenhouse effect. And so today we'll kind of be continuing on with historical climate, and then as I've been kind of matching this this lecture to the What Goes Up article from The Economist, please kind of follow along with that article. Some of these the slides, the ordering of the slides is kind of meant to match with the order of content in the article, and so I've added in some highlighting and some text. Written in some text on the What Goes Up article to kind of give you some pointers as to like what part of the lecture goes with what part of the article, to give you some more background to what the article is talking about. So we are here at the kind of talking about historical climate. So this is about the end of the first page and beginning of the second page, and to kind of wrap up, or to kind of reintroduce, I guess, what we were talking about before, is the Earth climate varies naturally for several reasons. We've seen this change over the 4.5 billion years that the Earth has been around, right? So there are a handful of primary reasons why the Earth's climate has changed over time. The sun, changes in the atmosphere, changes in the ocean. All right, and we'll talk about a little bit about each one of these in a little bit more detail, but as well, in something that I didn't mention at the beginning, are these cyclical variations in Earth's rotation and orbit called Milankovitch cycles, and that's what we'll focus on here in the next few minutes. Okay, so the solar output, right? The sun this is one of the potential changes in the change in historical climate. Is the amount of output that the amount of the radiation output up from the sun. All right, and so this the sun does vary in the amount of solar radiation it gives out on short and long-term trends or basis, but this variation overall is rather small in impacting Earth. Okay, so that is a change that happens over time, but it's the impact of the changing solar output is pretty small. We talked about atmosphere, changing levels in the greenhouse gas emissions, so water vapor, CO2, methane, aerosols are not greenhouse gases, but aerosols reflect light. So there's some atmospheric changes that happen. And then there are changes in the oceans, right? And we talked a little bit about how the oceans, there's the ocean circulation, like the global ocean conveyor belt, which transports heat around. But also kind of more multi-year variations like El Nino and La Nina, which also kind of transport heat and change how heat is transported by the oceans to the continents. And again, we should note that the oceans are a really important carbon reservoir. They hold roughly 50 times more carbon than the atmosphere. And they are soaking up some of our excess, some of this extra CO2 that we're pumping into the air. But this is leading to increased acidification of the oceans. It's making it more acidic. And this is having important consequences for corals and marine life, and we'll talk briefly about that a little bit more later on. Okay, so now those were some of the main drivers, right, of changing climates. Changes in solar output, atmospheric changes, changes in the ocean. But one of the other primary and most fundamental, most impactful changes is this historical variation in the kind of cycle of the Earth. And these are called Milankovitch cycles. So there are 3 different Milankovitch cycles. And they each have differences in how often they fluctuate. So I think the axial wobble and the variation of tilt, these first 2 change in the order of like 22 or 25,000 years going back and forth. And then that variation of orbit, letter C, that changes on the order of roughly every 100,000 years. Okay, so these are changing kind of at different time periods and interacting with each other in different ways. In these three cycles, there's an axial wobble. And so this is kind of, think of this as when you spin a top and the top starts to slow down and it starts to kind of wobble back and forth before it finally falls over, right? So that's an axial wobble. And so it's changing kind of the tilt of its direction from one way to the other kind of over time, all right? And that axial wobble has an important role in influencing these other two variations, the variation of tilt and the variation of orbit. So the variation of tilt then is kind of the Earth is not straight up and down like a top spinning completely. It is already tilted off to the side. And this is why we see kind of in the northern hemisphere during summer, they're daylight 24 hours a day, and in the middle of January, we would see nighttime 24 hours a day, right? Because it's tilted away. Earth is not perfectly straight up and down. It's tilted, and that tilt also changes over time, and so that's the second Milankovitch cycle. And when it kind of the tilt increases a little bit more towards that 25 degree, then that northern part of the Earth can receive more direct sunlight, and it's more likely to have more melting. And when it's tilted more closer upright, then it ends up receiving less direct solar radiation. And so this tilt varies over time. And the third tilt or the third change here, the third Milankovitch cycle is really important, and this is the eccentricity of the orbit, the variation of the orbit. So it changes from slightly more circular to slightly more eccentric, or like an oval, all right? And these three Milankovitch cycles kind of interact with each other to either kind of make the impact on the amount of solar radiation that the Earth receives. They kind of either moderate each other, or they can kind of work in tandem to accentuate the variation in the amount of solar energy that the Earth receives. And so these variations kind of work together over time, and leading to kind of bigger variations in the amount of solar radiation that the Earth receives. And this, in concert with kind of greenhouse gases and some of those other drivers of global climate changes, are responsible for the shifting climate that we've seen over time, right? And so these are powerful enough. These effects are powerful enough to really dramatically change how the effects of climate over time. And we've seen the recent history of the Earth over the past several million years or more, tens of millions of years. We've seen a real kind of stability, a strong trend, or periodicity, I guess is the right word, a strong periodicity to the Earth's climate, of entering periods of ice age and then these interglacial periods where we are now, where it's warmer, and then entering back into an ice age, and then where we are now in the interglacial. So you can kind of see that cycle here going on, where obviously the red indicates these warmer interglacials and the blue is indicating these cooler ice ages. And at the bottom you can see these are like hundreds of thousands of years time periods. All right, and you can see a map here of the extent of the ice sheets at the last ice age. So much of the northern hemisphere here was covered in ice, and there was some more expansive ice glaciers in parts of the southern hemisphere as well. All right, and so we were able to also determine that we were kind of at the tip. We had basically just reached the maximum kind of our temperature of that interglacial, and we're likely, based off of these natural cycles, heading back into an ice age. This would have taken many thousands of years, but that's basically kind of where we were headed based off of the natural cycle of things. based off of the Milankovitch cycles and those other climate drivers. And so how do we know that? Well, we have been scientists study the paleoclimate of the Earth. So this is the climate of the ancient past, paleoclimate. And we have detailed records of the climate that go back, 50 years, 100 years, anecdotal records that go back further, like from written histories, so from human history. But how do we know what climate was like 10,000 years ago or 100,000 years ago? Which is what we need to be able to determine these kind of periodicities in our historical climate. Check out your book. They have some great stories about this. We build up local indicators of these proxy indicators of climate and greenhouse gases. And so they can do things like drill ice cores, core trees, look at corals. They might drill into deep ocean sediments and muds, and look for changes in carbon dioxide levels, changes in pollen, changes in a variety of different things that can help them piece together kind of the climate at that time. And as I said, these kind of local indicators, these proxy indicators, are sampled locally all over the planet, and then they're compared, and they kind of compared together, and they build these kind of global consensus estimates of, this proxy indicator of, these tree rings over in Antarctica, or tree rings in Australia, tree rings in South America, this, ice core sample from Greenland. They all kind of say the same thing at the same time period, and therefore kind of the whole globe was experiencing these types of conditions, or warmer conditions or cooler conditions, what have you. Okay, so that's how they'd kind of put these things together. And they're able to put them together in really cool and pretty amazing detail. And here we've got really well constructed historical climate or paleoclimate for the last almost million years. And they're looking at some of the primary drivers. We know Milankovitch cycles are a primary driver, but they're also looking at these greenhouse gases and how they vary in tandem with changes in the Earth's temperature, right? And you can see an extremely strong relationship between the Earth's climate, the Earth's temperature, and methane and carbon dioxide levels. And so you can see how these have really changed in tandem with each other. There are periods of when CO2 and methane are high, temperature follows. When they're low, temperature goes low, right? And that's what is so concerning about these dramatic increases of red and green kind of going off the chart, right? So what's going to happen to temperature as these levels spike? All right. But it's not that simple, right? We know that there's a lot of feedback loops here going on, and that this is that these can really complicate how Earth's climate and how these different drivers of climate interact with one another. And I'll start the next lecture by kind of talking about this in more detail. But we've been introduced to negative and positive feedback loops before. And we've been tested on them. We know that negative feedback loops tend to promote stability. Positive feedback loops tend to promote change or acceleration towards extremes, right? So let's start thinking about how these different types of feedback loops, what type of feedback loops do we know of that relate to climate? All right. I will see you in the next lecture. Thanks, everyone, for listening.